In episode 6 of Mathematica Sessions, Discrete Math, today we're going to be looking at the basics of set theory and then later about functions, surjectivity, injectivity, and all that stuff. So if you're interested in that, stick around. It'd be great if you could write down solutions to these on paper and pen if you have some with you while I'm doing this, so that you can think about the problems too and not just me typing these things out. But anyway, okay, so let's begin. Maybe I better turn off the chime on this. I don't know if you guys can hear that, but it's chiming a lot. But we'll see how we go. Okay, so 7.1a. So we've got 4 sets here, A, B, C, and D. And we've got to write out the union, the intersection, the power set of D, and a Cartesian product for this. So we'll probably start by just saying what each of these sets are. Okay, so the power set of the empty set, so this is just the set containing the empty set and the set itself. So it's got 2 elements. And keep in mind, this is going to look a little bit messy, because we have sets of sets of sets and so on. Okay, so this is what A is, and now let's have a look at B. All right, so B is equal to the set containing the empty set and A. And so let's simplify this. So we have the empty set and A. Okay, so it looks like this. Now we still only have 2 things in this set B. All right, now C is the power set. I just have an ordinary P for this, but I mean the power set. It's usually a curly P. Okay, so the power set of the empty set is the set containing the empty set. And incidentally, power sets have a cardinality equal to a power of 2. So 2 to the power of the number of elements in the original set. So in this case, 2 to the power of 0 is 1, and we see we've got 1 element in this set C, which is the power set of the empty set. Okay, so now D is equal to the set containing A and B. All right, so we can do some copying and pasting here, because if we just take A and put it there. Okay, now we have A, but we also take the set B and we put it there. And so this set D still has 2 elements in it. It's just the elements are sets themselves. Okay, so now we can just go ahead and calculate various things. So C union D takes the elements of C and the elements of D and joins them together and eliminates duplicates. So we have the union of this set containing the empty set and the union of D, but this one right here is D. Okay, so what do these 2 sets, let's see, so the union, we take this one and we put it in, here, right? So actually what do I want to do? I want to take this, because that's the larger one. Say that this is equal to this, but now I'll include this empty set in it. All right, now it's a little bit tricky to look at, but you can see we have 3 elements in this set. Okay, good. Now let's go ahead and have a look at D intersect with B. So in this case, we're looking for what's common in both B and in D. Okay, and so in this case, I want to look at it from the point of view of the intersection of these two, where we've got the elements as sets themselves written out. Hang on, I just copied B, didn't I? So I need to put that the other way around, but that's okay. We can swap these around. All right, so this intersection then is just the set containing A. All right, and we could write that out if we wanted to. So this is the set containing this set right here. Okay, good. All right, now what are we up to? The power set of D. Okay, so the power set of D is the set of all subsets. Okay, but we want to look at that as the power set of the set that contains the set A and the set B, so that we don't have to write everything out. Okay, so we have a set. Now we always have the empty set in the power set. And then we're looking at the set of all, or the subsets of the set containing A and B. So the subsets are the set containing A, or the proper subsets, I should say, because the empty set is also a subset. Okay, and then we have the set containing both A and B, but we know that that is D. Okay, so this is a concise representation of the power set of D. Okay, great. And then finally, we have the Cartesian product of D with B. Okay, so in this case, again, I want to write it as Cartesian product of the set containing A and B, and I'll put times, but here you should list the elements of B in this set, but remember B is the set containing A and the empty set. Right, and now the Cartesian product is a set of pairs. So, windy outside. Okay, so we should have 4 pairs in this set. So we'll just write the pairs out. So we've got A together with A, and then we have A together with the empty set. Then we have B together with A, and B together with the empty set. All right, so that has 4 elements in it, and each of the elements in the pairs are sets themselves. All right, did you have a question? Thought I heard somebody speak up. If you have a question, just interrupt and let me know. Okay, so let's move on to the next one, which is true or false. I'll just make a little bit of space here. So true or false. Okay, so we want to see the sets for this one. So A equals B. Is this true or false? All right, so this one here is A. So this is A, right? And do we have this equal to B, right? And I'll just put a question mark there. Okay, so we can see that there are 2 common elements here, the empty set with the empty set, but is the set containing the empty set equal to the set A? Well, no, it's not, right? Because A is the set containing the empty set and the empty set itself. So the answer here is no, not equal. So false. Okay, now next question, is B a subset of D? Let's see, what is B? Okay, so B is equal to the set containing A and the empty set, and D is equal to the set containing A and the set containing B together. So is this a subset? I don't think so. No, right? Have I written this correctly? Yeah, so so we ask, is every element of B a member of D? And the answer is no, because the empty set is not a member of D. So no. Put this not in D. Okay, so that one is false. Okay, next one. Do we have C a subset of B? All right, so let's have a look at C. C is equal to the set containing the empty set. All right, and B is equal to the set containing A and the empty set. And so the question now is, every element of C also an element of B? And so the answer is yes. All elements of C, namely the empty set, are in B. So the element is right here, right? So yes, this one's true. Okay, good. Now, the next question is the intersection of A and D empty? Okay, so let's have a look. So A, this is A. And then D is equal to this set. All right, so do these sets have any common elements in them? Now, so let's look at the elements of D. We've got two elements in D, this one and this one, right? But none of those are common. So, so yes, intersection empty. Okay, good. Any questions? It took a while. Can you guys still hear me okay? All right, I'll take that as a yes. So let's have a look at 7.2 now, which says, prove by contradiction for all sets x, y, and z, the set difference, the intersection of these set differences is empty. All right, so what we want to do here is prove by contradiction. So we'll assume that the intersection of these three is not empty. Okay, so assume not empty. Okay, so if we assume that this is false, and assuming that it's not empty, then what we're doing is we're assuming that there's an element in this intersection of these three sets here. And since that's an intersection, what we're doing is assuming that there's an element in x minus z, an element in y minus z, and an element in x minus y. So I'll say we assume that there is an x belonging to each of these parts. So x belongs to this one, and x belongs to y minus z, and x belongs to the other one, which is x minus y. Okay, now reiterating what this assumption means. So what we have is that little x belongs to big X, but doesn't belong to, and I'll look for the symbol here in my palette. I don't see it straight away, so I'll just put not in. So not in Z. And likewise, so that's that one, right? So it's in a big X, but not in Z. And now this one here says also X is in Y, but not in Z. So just copy and paste, and X is in Y, but not in Z. Okay, and then the last one says that X is in X, but not in Y. So X is in big X, but not in Y. Now the last piece is contradicting this right here. And so what we do then is say a contradiction since X is in Y. Okay, and so that means that the original assumption is false. So assumption false, hence the set is empty. And so I'll just copy and paste this statement. Okay, and that's the end of that proof. Okay, so let's have a look at the next one then, unless you have any questions. All right, so the next one says, prove the following using De Morgan's laws for any sets A, B, and C. Okay, now you remember what De Morgan's laws say. They involve turning an X and Y with a not in front into not X or Y, and vice versa. Okay, but here we get a couple of hints, all right? So the hints are that X minus Y is equal to the intersection of, and so I'll just pull up the button for this, intersection of X and the complement of Y. And that we can express with an exponent there with a C. Okay, so that's the universe without Y. So the intersection of these two. All right, and then so that's the set difference. And now we also have the hints of what actually, or how to use De Morgan's laws. So that would be that the union of, hang on, what I want to write is X union Y, so I can keep these letters separate. Okay, so the this union complement is equal to, because this complement is acting logically like a not. Okay, so this is equal to the complement of X intersect with the complement of Y. All right, and then the other way around too, the other De Morgan's law. So it looks a lot the same, except we just swap the symbols. Okay, so these are the hints that we'll use here, and then the rest pretty much follows, right? So what we do is we'll just take the left-hand side first, and just say that this is equal to, okay, so we want to use this rule here, except for the first one is the difference, and then the second one here is the set C. Okay, and then we can simplify this again, replacing A minus B with this right here. So the intersection of the complements. So A intersect the complement of B. Okay, and then finally we can take off the brackets because we have associativity of this intersection. All right, and so now let's look at the other side of the equation. So the other side of the equation, now using the same ideas, so we have a set difference here, so we use this. Okay, in the first one I want A, and in the second one I want B union C in place of the Y. All right, and now we can use this rule right here, replacing the B union C complement with the intersection of the complement of B and the complement of C. Okay, and we can see that these two straight away they're the same. So in other words, these are equal. And that's the end of that proof. Okay, any questions on that?
I want to ask a question.
Yeah, go for it.
Will the loss of the sets be given in the examination, like the logical equivalence loss?
Do you mean this?
Yes. Will this be given in the examination?
I would think so. Of course, I'm not the one who decides that, right? It's the person who writes up the exam decides that. So I can't tell you right now, and in fact, they probably haven't even made it yet until after the break. So maybe after the break, you should ask your lecturer or coordinator what they'll give you on the exam, as in, will they give you all the logical laws? So I doubt it, because they typically don't have all the rules like De Morgan's rules for logic and so on at the back. However, the lecturer may give you this sort of thing as a hint in the exam. That's possible, right? And so, of course, I don't know. It's kind of up to how difficult they feel the exam should be at the time, right? So
Okay.
that's typically the case. All right, so any other questions about this one? Okay, so let's have a look at 7.3. So this one says, define the set S. Now I'll just say that these kinds of problems, they're frequently on Math 7861 exams. So you might want to pay attention to these kinds of recursion problems. And they always give people a headache for some reason, right? Because they're kind of unfamiliar to most. Okay, so it says there are basically three axioms. Now I've kind of abbreviated this. So the first one says that the pair 0, 0 belongs to the set. The second one says if A, comma B belongs to the set, then so does A plus 2, comma B plus 3, and A plus 3, comma B plus 2. And then the third axiom says there are basically no other elements that are not obtained in these two ways in the set. And then we're asked to find subsets of S obtained from 5 iterations of these recursions. This is a kind of unusual question. So the way you go about it, and so what I have here is a little bit of code, and so I'll run the code in a little bit. But let's just talk about this, because you would do this by hand. Okay, so the way you would do that is you would say, on the first level, what you have is just the set containing 0 and 0. So this one right here that I've written. Except you see I've put this in Mathematica code, incidentally, so that I could run that. And so I need to put a curly bracket around the 0, 0. All right, now, so what happens is in the first iteration, we take 0, 0 and we add 2 to the first element or component and 3 to the second one. And so we'll get 2, comma 3. And then we'll go and add 3 and 2 respectively to each component, and we'll get 3, comma 2. Okay, so just by hand, we would just think about where I want to write. So we would have, say, S subscript 1 being equal to 0, 0, right? And then S subscript 2 equal to, let's see, so we've got 0, 0, and then we obtained 2, comma 3. Whoops, I'm trying to write the round brackets here. And then we get 3, comma 2. Okay, now if we apply the same rule to these, right, we don't get anything new from 0, 0, but we do get something new from each of these other ones, the new ones. So in this case, what we do is we take the new ones and we apply this rule here to those. Okay, so we still have We still have this in our subset, but the new ones that we get at this point, we get 2 from the point 2, 3. And so adding 2 to 2 and 3 to 3, we get 4, 6. And then from the other one, we get 5, 5, right? 5, 5. Okay, now from 3, 2, we get 2 points. So we get 5, 5. And then we get 6, 4, right? But we don't want to write 5, 5 twice. So we just include the 6 and the 4 here. Okay, and so on and so on. So now I'll just show you what it looks like when I run the code on this procedure. So I'll uncomment it here, and then I'll just press the button. But you can see what I'm doing here. This is the second part of it, adding 2 and adding 3. And in this, I'm just indexing. I'm pulling out particular elements, like the second coordinate in this case, and the first coordinate here. And then I'm just iterating as k goes from 1 to the length of s and forming a list. In this part here, I'm just restructuring the list. And then in the final part, I'm declaring the new s to be the union of the old s and basically the new parts that I've found. So I'll run this, and so you can see what we get. So you can see 0, 0, 2, 3, 3, 2, 4, 6, 5, 5, 6, 4, and then the other ones obtained in that way. So just scroll down so you can see it there. Okay, good. So let's move on to the next question, unless you have any more questions. Okay, 7.4a, prove or disprove. So these are all in 7.4, prove or disprove. But the first one says, for all sets A and B, is the power set of the union of A and B equal to the union of the two power sets? Okay, and so you might play around with this. If this were an exam question, you might think about it for a little bit with some examples and see whether or not you suspected it to be true or false. Okay, so this one here is going to be false, and we can give it a simple counter example. So let's just say let A be equal to the set containing 0, and let B be equal to the set containing 1. Okay, and now let's take the union. So the union of A and B is equal to the set containing 0 and 1. Okay, and so now the power set of that union is equal to the 4-element set containing the empty set, then 0, then 1, and then all of the entire set A union B. 0, 1. Okay, so this is the power set here. It's got 4 elements in it. On the other hand, the power set of A has 2 elements, and so does the power set of B. So this is, power set of A is the empty set together with all of A, right? The set containing 0. Did I get that right? Yeah. Okay, great. And then we need the union with the power set of B, but that looks similar, okay, because we just have the empty set and then we have the set containing 1 in that. And now when we take the union of these two, we've got the empty set there twice, right? So we have a 3-element union. The empty set, the set containing 0, and the set containing 1. Okay, so of course the power set of A union B is not equal to this, because you can clearly see that they're different. It's missing this set containing both 0 and 1, so not equal. Okay, so that's A done. Now let's have a look at B. Prove or disprove. For all sets A and B, the power set of A equals to the power set of B if and only if A is equal to B. Okay, so let's start off one way. So remember, this is a two-direction implication. So let's start with the easy part. So we can just say clearly, if A is equal to B, then they're going to have the same power set, right? Because they have all the same subsets. Then the power set of A is equal to the power set of B. Okay, conversely, if we are going to assume that the power set of A is equal to the power set of B, how do we show that A equals B, right? So maybe that's a little bit more tricky. So let's just say to show that if the power set of A is equal to the power set of B, then A equals B. And I'll just put a colon here, right? Because this is an implication. Let's just even put a bracket around this. So to show this, what we're going to do is assume, so we'll assume that the implication is false, meaning the premise is true and the conclusion is false. Okay, so we'll assume this while A not equal to B. Okay, so and so this is to assume here that T implies F, right? So this is a proof by contradiction that I'm setting up on the converse. Okay, so under that, then we can say, without loss of generality, so this is a maths way to say that, there exists an element x of A that is not in B. Okay, because we're assuming that A and B are not equal. And so you could assume that, I mean, the reason that we write without loss of generality there is because you could equally well say that there's an element x of B that is not in A. Okay, so when you, it's a simple mechanism to simplify the proof, or eliminate setting out unnecessary cases. Okay, so continuing, we assume that there's an element x of A that is not in B. Okay, so this means that the set containing x belongs to, where is my symbol for belongs to the power set of A, but not the power set of B. Just put a not in front of that. But the set containing x is not an element of the power set of B. Okay, and so what this means is the power sets cannot be equal. So hence, the two power sets cannot be equal. So I'll put not equal. And so this contradicts. So a contradiction to the fact that we assume that they were equal. Okay, and so we must conclude now that that this is true. So all right, therefore, if the power sets are equal, then the sets are equal. Okay, and so we've gone both directions in that. And so say we conclude that the power sets are equal if and only if the sets are equal. Okay, great. So let's have a look at 7.4c, prove or disprove. There exists a set A such that these are the elements of this power set of A. Okay, now straight away it looks plausible that the set could be the set containing A, B, and C. But that's not the case, right? Because the power set must contain the empty set. So let's note that. Okay, so false. Power set of A must contain the empty set. And this one doesn't, right? And so as well, you can just count the number of elements. Here we've got 7 elements, right? But power sets have to have a power of 2 elements as well. So you get a hint just by counting. All right, 7.4D, prove or disprove. Let A, B, and C be sets. If B is a subset or equal to C, then the Cartesian product of A with B is a subset or equal to the Cartesian product of A with C. All right. So in the first case, so we have 2 cases here. So let's first assume that A is empty. Okay, so if A is empty, then the Cartesian product of A with B is empty. This is empty. And likewise, the Cartesian product of A and C is empty. And since the empty set is a subset or equal to the empty set, so we have this holding true. So it holds true. Okay, and then we just say similarly, if B is empty, B or C is empty, then we get the same result. Okay, so next, our next case is assume each are non-empty. Okay, so then basically we're assuming that we have an element, okay? Assume that they're non-empty, and we're assuming the premise, because we're going to do a direct proof. So we're also assuming that B is a subset or equal to C. And so in this case, we're assuming that B has an element. Then B, little b, belongs to big B, hence little b belongs to big C, because big B is a subset or equal to big C. Hope I said that correctly. Okay, so then what we see now is that letting little a belong to big A, if A comma B belongs to the Cartesian product of A and B, then it belongs to the Cartesian product of A and C. Okay, because of this right here. And so we're treating these as arbitrary elements of A cross B. Okay, so true, that is a subset or equal. And we've proved it. Okay, so that's just about all on sets. Now let's start to look at functions. So 7.5, consider the function f mapping real numbers to real numbers given explicitly by f of x is x squared minus 1. Okay, and so we've got a number of questions here, right? The domain, the codomain, and the range. Look, it might be handy just to plot this function because I can do that. So x squared minus 1, and let's just choose some small range, like minus 3 to 3. Or actually, let's go a little bit beyond that. All right, so this is what this looks like. Now the domain, it's a set of all inputs, and it's actually given to you in the description of the map, right? So let's see, I'll make this smaller now that we know what this looks like. And then I'll just write right under this, okay? So the domain is equal to, maybe I'll put dom for domain, is equal to this set, okay? And it's always that set there. Okay, now the codomain, that's the other set. So that's easy too. I'll just put codom, also equal to the real numbers, but the range of f is what comes out of this, okay? So the range, I'll just use curly, just plain R, range equals, now it's what comes out. So we can just look at the y-axis here. So this bottoms out at -1 because when you put in 0, that's where this function is least. And let's write it in interval notation. So it starts at -1, and then the top of it is infinite, but we need a round bracket because infinite is not a number. Okay, so that's our range because it keeps going up. Okay, now what is the image of the map, or sorry, image of this set under the map F? All right, and so we just look at what comes out of this when we restrict the domain to -1 up to 2. So we can even do this with a plot here. Or you could just think about it, right? So -1 to 2. And so the question is, what comes out? What kind of numbers come out? So we've got -1 up to 3. Okay, so I am F in this case is equal to -1 close bracket up to 3 close bracket because we include the endpoints. Okay, next one. What is the pre-image of this set from 0 to 3 inclusive under F? Okay, so this asks if these are on the y-axis from 0 to 3, where did these come from? Okay, so 0 to 3. So now I want to plot more of this, right? So let's just go -4 to 4 again. Okay, and so we're asking, how do we get out 0 to 3 from this function? Okay, so where does this occur? So you can see that when x is 1, this intersects the axis and goes up. And likewise, when x is -1, we intersect the axis and it goes up beyond that. So the pre-image in this case is a union of two sets. Okay, so starting with starting with 1, and then when we input 2, we have 2 squared is 4, subtract 1 and we get 3. So that's on that side, and then on the other side, similarly, so -2 up to -1. Okay, so this is our pre-image of the map. Okay, great. So, right, I think that's all I have for that one. Now let's have a look at 7.6. So 7.6, we've got a map from the integers to the integers given by f of n is the floor function of 1 minus 6n all over 3. And the question is it 1-to-1? Is f onto, and then prove or disprove f of mn is equal to f of m times f of n. Okay, so is it 1-to-1? So the way we proceed to show that it's 1-to-1 is we say something like assume f of m is equal to f of n, and then we try to show that n is equal to m, or m is equal to n. So in this case, what we're assuming is that the floor of this, when we put an m in here, is the same as the floor of this when we have an n there. Okay, but we can simplify this. So simplifying, what we have here is, because this floor is equal to the floor of 1/3 minus 2m, right? So we'll say that this is equal to the floor of 1/3 and then subtract 2m, right? But since 2m is an integer, this is equal to minus 2m plus the floor of 1/3. But the floor of 1/3 is 0, so this is equal to minus 2m, an integer. Okay, so essentially what we're assuming then is that minus 2m is equal to minus 2n. And so now we see straight away dividing by minus 2, hence m equals n, so f is 1 to 1. Okay, next question, is f onto? All right, so is f onto? Now that we know what f is, so f of n is equal to minus 2n, we can see that this produces even numbers. So say produces even numbers only. Okay, and so given that's the case, odd numbers don't come out of it, and so no, the function is not onto. Not onto, meaning surjective. It's not surjective, since f of n is never odd. And the integers do contain odd numbers as well, of course. All right, let's have a look at the next one. Prove or disprove f of mn is equal to f of m times f of n. All right, so let's rephrase this. So this would say that minus 2 times mn is equal to minus 2m, and we need a bracket because we're multiplying now, times minus 2n. Okay, and so let's simplify the right-hand side, and so we get 4mn. So of course this is not true in general, right? Not unless they're special or particular numbers, right? So this is not true in general, so we'll be able to find a counterexample. So I'll say false, put m is equal to 1, say, and n is equal to minus 2. Okay, and you'll easily get a counterexample there. Okay, great. Any questions? All right, so let's see. Do I have any time to do another one? All right, so this one, here we've got a set containing 1 and 2, and a map mapping the Cartesian product of A with itself to the integers given by f of AB is equal to A times B plus 1. Determine the image of the map, basically. All right, so basically what we need to do is see what it does to each of the elements in the Cartesian product. So in other words, f of A cross A, and we can just list the elements of A cross A, because they're just pairs. So we've got 1 with 1, we have 1 with 2, we have 2 with 1, and then we have 2 with 2. Okay, and then applying the map to each of these, we get the numbers 2 for the first one, right, because that's 1 times 1 plus 1 is 2. And then we get 3, and then we get 4, and then we get 6. Okay, and so we've done that. We've determined the image of the map. All right, and likewise, that is just the range, right? So the range also is the same thing because that's what comes out. So we've also done C. Okay, so the next one, is f 1 to 1? Is it onto? All right, so remember the technique for proving 1 to 1. You assume that f of one point is equal to f of the other point, and then you've got to show that the points are equal. Okay, but in this case, what you want to do is note that every input of the function here has exactly one output, and you can see that just from this right here, right? So yes, it is 1 to 1. So yes, 1 to 1, one input, one output. Okay, is it onto? Let's see. No, it's not onto. Okay, so but not onto, because this set right here is not equal to. So not equal to the set of integers, right? Some of the integers are missing in this set. In fact, very many, infinitely many are missing in this set. Okay, great. We got through 7.7. I wonder if we can just spend a little bit more time and get through 7.8. So this one I think I can just talk through without writing much. So we've got a map now. They're all given by the ceiling function. And so that's like the floor function, except you go up when it's less than an integer. So the smallest integer greater than or equal to x. Okay, so they're all given by that, except the in this case, the domain and the codomain are different sets, various sets. All right, and the question is, are these one-to-one, onto, or bijective? So the first one is neither, right? So you can easily, oops, neither. You can easily find counterexamples because you're dealing with a floor function, right? So picking various real numbers will show you that it's not one-to-one, and of course not onto either. Okay, because you're not getting you're only getting integers out of the function, right? So numbers like pi are never met, so they're not in the range of the function in this case. All right, next one. Now we have real numbers to integers. So this one is onto because you do get every integer out of this, but it's not one-to-one for the same reason as A is not one-to-one. So this one is onto but not one-to-one. Okay, now C, here's domain is integers, but the codomain is real numbers. All right, so this one is now one-to-one, so you can prove that it's one-to-one using the technique, assume f of m is equal to f of n, and then you can deduce that m has to be equal to n because the domain this time is integers. And so in other words, in this case, since the domain is integers, these are just, the function is just x, right? Yeah, I think so. Okay, so it's one-to-one, but not onto. Okay, and then the last one, likewise, this will be one-to-one, and it will be onto because the codomain here is integers, so every element came from somewhere. So this one is yes, bijective. It's both surjective and injective. In other words, onto and one-to-one. So yes, bijection. Okay, great. Now, I think I can quickly do 7.9 and then we'll just be finished. Okay, so this one here, we've got the set from 0 to 4, and then we've got two maps from A to itself, F and G, and we're asked, is the congruence? So this is congruence. F of A congruent to A plus 4 all squared mod 5. Is this the same as the map sending A to A squared plus 3A plus 1 mod 5? And the answer is yes, and it's really simple to see. So let's just expand this one, all right? And so I can even do this with code here. Just write expand, but it's pretty obvious what the expansion is. Okay, so we get this expansion. So these two are equal, all right? And then I'll put an equals equals when we take congruences. So equals equals, meaning congruent, that's normally 3 horizontal lines. So all I have to do is reduce the coefficients mod 5, right? And so 16 is 1 plus 15. So mod 5, that's 1, and then 8 is 3 plus 5, so that's 3a. And we still have the a squared. Okay, and then we need to write mod 5. Oops, mod 5, not mod 6. Okay, so since those two are congruent mod 5, we see that the maps must be the same. So yes, f is equal to g. Okay, great. I think we got through basically 99% of this problem set. So thanks, guys. Do you have any questions at this point? All right. Sorry, Sachith, I see your question now. Does every set have a null set or empty set? Well, Sachith, every power set should have the empty set in it. So every set has the empty set as a subset, okay, but it doesn't have it as an element necessarily. So sorry about the delay in answering that question. Okay, Jeremy says, can a set have two same elements? Well, technically, Jeremy, no, you don't want that. And I'll just give you an example here. So because I'm playing with code here, right? So if I just write this 1, 2, 2, 3, minus 7, all right? So here, what I have is, it's really acting as an array, right? It's a list of numbers. But if I want to take that as a set, I can just apply union to this, right? Because sets should not have the duplicates in them. Okay, and so this is how you would write the elements of the set. So no, you don't want duplicates in your set. Did I answer that question right, Jeremy? Yeah, okay, sure. So yeah, you want to get rid of the duplicates when you're dealing with sets. And incidentally, this software language that I use here, Mathematica, it uses these set brackets, but it uses those to refer to arrays, whereas set brackets in mathematics means for sets, right? Generally speaking. Okay, guys, it's about time to knock off, so thanks.